Hello, everyone, and welcome to today's Geoscience Online Learning Initiative webinar course. I'm Leila Gonzalez, and I'll be moderating today's webinar with Christopher Keene, who is also joining us from AGI. And I'm pleased to introduce Chris Braaten, who will be our instructor today. Chris is a PG and CPG and is also a Senior Petrographer Geologist at American Engineering Testing Incorporated. He graduated from the University of Minnesota-Duluth with degrees in Geological Sciences and Environmental Studies. He has spent 15 years with American Engineering, holding positions in the Construction Materials Department as a field technician, bridge inspector, and Aggregate Laboratory Coordinator. And for the last 9 years, he has held a petrographer position in the Petrography Chemistry Department. He has performed petrography on construction aggregate from 46 U.S. states and 17 different countries and territories. And with that, I'll go ahead and turn the slides over to Chris.
All right, thank you. All right, I want to first say thank you to our sponsor, Joel. It's pretty cool that they were able to do that. And then I heard that we have just about 1,000 people who registered. So I want to thank everybody for signing up and getting ready to listen to this presentation. So as I was saying, this is the Introduction to Forensic Geology and Petrography. And this is intended to be, as my wife likes to say, a high-level overview of our discipline. Not a lot of people have heard about it. I certainly didn't learn about it. A lot of this stuff in college at my university, how different aggregates and minerals react with concrete. So a lot of my training was on-the-job training. But we'll get into that and let's get going. So the first couple slides, I apologize, I am going to read off of. And then we'll get into photographs because that is one of our main things we like to put in our reports is photographs of everything. So first couple slides, just read off of. And first slide is, what is forensic geology petrography? So petrography is a geologic term applied to the microscopic analysis of rock. The science can also be applied to concrete and other cementitious materials. Forensic geology is using geologic principles to look for reasons why a material or structure is exhibiting problems. So a few of the standards that we follow, they're compiled by the American Society for Testing of Materials, or ASTM. You'll hear me say ASTM quite a bit during this presentation. So if you're not familiar with ASTM, you can start looking at different things and you'll see it everywhere. I even have seen it on my son's Play-Doh. So they do a lot of different standards for stuff. So some of the ones I'm going to be going through though is ASTM C294, which is the descriptive nomenclature for constituents of concrete aggregates, and C295, which is the standard that we follow for petrographic analysis. A couple other ones are ASTM C1721, and that's petrography for dimension stone. ASTM D4992 is petrography for riprap or erosion control materials, and then ASTM C856, which is petrography of concrete. So typical petrographic qualifications are have an education, a degree in geology, typically. I say typically because I have met some engineers that do petrography. And then mentoring, which is the ASTM standards state all petrographic examinations be performed or supervised by a petrographer with at least 5 years of experience in petrographic examination of concrete or concrete making materials. So why use petrography? Construction aggregate quarries and gravel pits use it to determine if they have or how much potentially deleterious problem-causing substances exist in their source. The same thing can be applied to dimension stone, such as veneers, pavers, etc., and riprap or erosion control. You also can do troubleshooting hardened concrete and masonry problems, condition surveys and rehabilitation of structures, quality control of construction materials, and get the occasional research and development. So we'll start with the petrographic examination of of aggregates, which is ASTM C295. Some examples of potentially deleterious substances in aggregates are shale, coal, chert. Chert can be twofold. One, you can have hydrous chert, which is really soft and very porous, and that can cause pop-outs at the surface. We'll talk about pop-outs later. Or it can also do internal damage, such as Alkali-Silica Reactivity, which again, talk about in a few slides. So then you can have the minerals, quartz, which is microcrystalline or strained quartz, opal, chalcedony, volcanic glass. Volcanic glass is highly reactive, or tritomite and cristobalite, which are high temperature forms of silica and volcanic rocks. Those can cause alkali-silica reactivity. Micaceous minerals, they can increase the water demand or have a poor bond to the cementitious paste in concrete. Pyrite and pyrrhotite can produce staining accompanied by volume increase. And then gypsum can cause internal sulfate attack. So those are just a few of the minerals and particles that we might look for in an ASTM C295 petrographic analysis. Some of you might be wondering, if you've never heard of this, why is it being done? Maybe why haven't I heard of it? I got these statistics from the United States Geological Survey, and they put these out quarterly, and then they do an end of the year one. So just to show you the volume of construction aggregate used in the US, in 2019, 1.53 billion tons of crushed stone valued at more than $18.7 billion was produced. Those are staggering numbers to hear, and the volume is crazy. Of the total domestic crushed stone produced in 2019, it's about 69% was carbonate, limestone, and dolomite. 15% was granite, 6% was trap rock or basalt, 5% miscellaneous, 4% sandstone, quartzite, and then the remaining 2% was divided among a bunch of different things. So separately from crushed stone, they also use sand and gravel, and these sand and gravel operations in 2019 contributed 970 million tons of construction sand and gravel, valued at more than $9 billion. So I highlighted the leading states. Obviously, my home state, Minnesota, is always in the top 5, not always, but typically in the top 5 for sand and gravel production. A couple reasons for that is that we had some glacial activity in the past that left really great sand and gravel deposits, and a lot of it happened to be near our metropolitan area. So a lot of our metro area, the Twin Cities, St. Paul, Minneapolis, has been built using sand and gravel in concrete. So the difference is, if you're not familiar, crushed stone comes from a quarry. So you're mining a hard rock body. Sand and gravel is just operated out of a pit where they're basically just digging it right out of the ground. They might have to do some other processing to it. Some people crush it. Some people, most operations wash it. But there are differences between quarries and pits, crushed stone versus sand and gravel. So this is a picture of my start of an ASTM C295. And I like to get this out of the way right away. That is not beer up in the corner. It is coffee, the essential liquid of a geologist. We have cold pressed coffee on tap, keep us nice and alert while we're doing our technical observations. But so as you can see, those for this particular slide, those are thin sections of different rock types that I picked out of a natural gravel from Arizona. So in a gravel, you can imagine it's got, several different lithologies that you might encounter. And your job is to pick out differences, like different lithologies or different textures, different colors, and see what you have. Most of the time you can lump, some rock descriptions together, but you want to get a nice broad spectrum of what you're actually looking at. And you might get let's say I get a quarry from of granite, I might only make 4 or 5 thin sections. So gravel is a little bit more intense just because there's a lot more lithologies present. Now, typically, a C295 is recommended every 3 to 5 years for aggregate producers. Some people do it more frequently. I have a client that does it quarterly, and I'm not sure why they do it quarterly, but it could be because of specifications call for it, or whoever they're selling it to, their product to, could require them to do it. A lot of times, though, it's once every 3 to 5 years for the most part. So after you get your thin sections and you start going through those, you start identifying your lithologies, then you'll do a gradation with US standard sieves, typically for concrete coarse aggregate. You use a 1 inch, 3/4 inch, 1/2 inch, 3/8, number 4, number 8 US standard sieves. So you get a gradation, and on each sieve, you want to split that down to approximately a minimum of 150 particles. So then after you get your thin sections analyzed and you have rock names for all those, then you can start to compare and contrast your hand sample of 150 particles. So then you'll give your client a breakdown. You have 30% basalt, 20% granite, 10% this, and then you can start breaking down any other deleterious stuff. Maybe you have 1% shale, and you make comments about that. But it all starts with the thin sections and getting good rock descriptions and photographs of any reactive textures. So that previous slide was for the coarse aggregate. The fine aggregate, we also do thin sections for fine aggregate, but obviously that's a lot smaller material and it would be a nightmare to do that many thin sections. So what we do is we make an epoxy plug of the sand grains from each of the sieve sizes, and for concrete sand, they typically use a number 4 sieve, number 8, 16, 30, 50, 100, 200, and then whatever's below the 200, called the pan material. So you make the number 4 and number 8, you can typically do that as a hand sample underneath our stereoscope. Otherwise, we do make thin sections of everything passing the number 8. And when you're looking at the thin section for sand, you try and get a point count of 150 particles and no rock descriptions, but what you're just doing is taking a tally. I just crossed a granite, I just crossed a basalt, I just crossed a mineral quartz, feldspar, whatever it might be. And then you'll get a tally and you'll get a weighted percent of how many lithologies and what particles are in there. So the picture on the left, that's a natural sand. Natural sands obviously are going to have a lot more lithologies or minerals in it to identify. Producers also do make manufactured sand, which is from what we talked about, quarries. So a quarry will crush down their product to a sand to meet that gradation standard. So there's a couple different reasons to do this. One of the main reasons I know that I visited a quarry, an area of North Carolina where they don't have much natural sand that would meet those concrete gradations. So they do manufacture their stuff their sands out of a rock body, out of a quarry. In Minnesota here, the difference, we have so much sand that typically in our sand and gravel pits, we get about 30% gravel, which means any rock typically retained above the number 4 sieve or 4.75 millimeters or higher. So that's coarse aggregate, you would call it. And we get about 30% of that in a good sand and gravel pit. So that means we have 70% of that is sand. So typically what happens, they just can't sell all that sand, so they use it and they'll just backfill in their sand and gravel pits. As they mine out that gravel, they'll backfill with that sand as they start their reclamation process. So it is interesting to learn the differences between the geographic regions and how how different producers have to deal with either a surplus or a deficit of certain materials. So another type of aggregate is lightweight aggregate, and this is pretty cool stuff. I posted a hand sample photo. This is a photo of it, or an image of it in concrete. The thin section of lightweight aggregate is not that entertaining, right? It's glassy, it's mostly opaques and isotropic, so it doesn't make for a great thin section, but it is a cool product and we do get it occasionally. And if you're not familiar, lightweight aggregates are, they're made out of several different things. They can be natural. Pumice and perlite are natural lightweight aggregates. This one that you're looking at here is actually a manufactured aggregate. It was mined as a shale, and then the shale, it's called expanded shale. The shale is heated to about 1,000 degrees Celsius, and then the gases generated expand the material. So it creates all those bubbles. It creates a glassy texture in it. So, and the reason people make lightweight aggregate and use it, they typically use it in building structures because it can reduce the dead loads from floor to floor on like high-rise buildings if they're doing that, and can produce a lot of savings in building foundation and other reinforcement. So it is pretty neat engineering. Okay, so here's start looking at some of the minerals that we might see and call out. So this particle on the left here, that is in concrete, it's a metamorphic particle, and it's got the mineral pyrrhotite in it. Pyrrhotite is not as common as like a pyrite, but it's definitely oxidizes more rapidly, and it can create expansion and different issues like that when it starts to oxidize. You can see, so all of these white arrows we have are places where we took microprobes and used those and identified pyrrhotite in our X-ray diffraction machine. And then the red dashed lines represent some microcracking that has started because of the expansion of the pyrrhotite, and you can see the microcracking does propagate into the concrete. And on the right photo is a zoomed out photo where you can see that radial cracking from the expansive properties of this. Now, pyrrhotite has become very popular to talk about in the last several years, particularly on the East Coast. They had a lot, and this isn't any proprietary information or anything, because there's a lot of news articles written, but they had a lot of issues in residential foundations. They started to like crack and kind of fall apart. People were wondering why, and they did trace it back to the mineral pyrrhotite, and then they also traced it back to one single quarry where they were mining this pyrrhotite. But because of this, and because of all of the deleterious nature of pyrrhotite and all the destruction that it might have caused, and different rebuilding of possible foundations for homeowners, I know the USGS, the United States Geological Survey, just put out this year a generalized map of where you might find the mineral pyrrhotite in rock bodies around the country, around the US. So as I said, also mineral pyrite does have expansive properties, not as rapid as pyrrhotite, but it can. So this photograph in the upper left here, those are stone veneers on the outside of a residential home. And you can see that staining that's happening. Not pretty. Obviously, the homeowners wanted to know what was going on. So we got it, took some photos. You can see the one below it here, where the laser pointer is, started to get this really nasty pitting from the weathering of pyrite. Up here, this is a cross-section view where you can see like a honeycomb texture of pyrite when it's starting to react and cause nasty things to happen to those really nice veneers. And again, this other picture here, cross section of a stone that was not used in service. So there was no reactivity, but all these little brassy spots are pyrite. I mean, that's a lot of pyrite. So the stuff in the body of the rock, not exposed at the surface, most likely wouldn't do anything unless that stuff on the surface started to react bad enough and maybe cause like planes of weakness or seams or cracks for water or atmospheric conditions to start to touch some of these lower ones. And then it's going to start to, you know, expand and possibly destroy some of these nice rocks used on this wall. So pyrite is something we call out during our observations. In concrete, it can cause staining. I have seen it cause staining, but it does take has to be at the surface, and like I said, and for it to really start to oxidize and cause that nasty brown stain. All right, another one we look for is micas, and I'm just going to read this on the side here. So per ASTM C294, which is that descriptive nomenclature, because micaceous materials have a high surface area, they can influence the properties of freshly mixed and hardened concrete. Aggregates with a high mica content can reduce workability and increase the water demand of the concrete. The shape and perfect cleavage of micaceous minerals may result in a poor bond to the cementitious paste. So this photo, this photomicrograph here, contains a lot of, it's a manufactured sand, it's a crushed granite, and all those green arrows represent muscovite. The red arrow here is pointing out some strained quartz. We'll get into that a little bit later, but that's a lot of mica and it can cause problems. So it's something we definitely documented. All right, now we have alkali-aggregate reactive textures. So there are two types of alkali-aggregate reactivity or reactive textures. There's alkali-silica reactivity, ASR. There's also alkali-carbonate reactivity, ACR. These photos, these images, I'll talk about ASR. So alkali-silica reactivity. This image on the left here is of a chert particle, and the red arrows are showing beautiful chalcedonic quartz, that nice fibrous radiating texture of chalcedonic quartz that you see quite a bit in cherts. Also, you'll notice the matrix is cryptocrystalline quartz to microcrystalline quartz. So chert can be highly reactive with alkalis in the cement paste and concrete. I'll get into some of the destructive. I have images later on that shows some of the destructive nature. But so the silica in these rocks, certain types of quartz, certain other types of silica can react with the alkalis in cement when they're mixed together as concrete. So it can produce an amorphous precipitate we call it ASR gel, because it is like a gel-like substance that starts to propagate out of different aggregate particles, and that gel will absorb water and expands, and it results in characteristic crack patterns, which again I'll show you. But so that's one of the minerals that we definitely look for, and when you're doing the particle count of the C295, the hand sample stuff, you'll definitely want to count, like, you have 5% chert. You probably should get your aggregate checked to see if it has alkali-silica reactive expansive properties. And there are other tests that can be performed, physical tests that can show those expansive properties. The picture on the right, that's of a garnet gneiss, another type of quartz that can cause that alkali-silica reactivity is microcrystalline quartz or strained quartz. These red arrows are pointing to strained quartz, and if you're not familiar, typically if you're looking down a scope and you see quartz and you rotate the stage, it has a nice unit extinction, meaning it goes light to dark or white to black almost immediately. These strained quartz particles have what's called an undulose extinction or wavy texture. So it won't go extinct right away. It just kind of does this wavy. You can almost see it right here, how there's a different gradient of color through that quartz mineral, if you're following my laser pointer. So that's an indication of straining that happened from whatever reason. If this is a gneiss, so some kind of metamorphic issue happened and strained that quartz. So we do call that out. And these blue arrows represent garnets because they don't really affect concrete at all, but we're geologists, so you definitely want to point out anything cool you see. All right, so this next slide, this is alkali-carbonate reactivity. So alkali-carbonate reactivity is a little less known. It's less common than ASR, and it's much less understood about alkali-carbonate reactivity compared to alkali-silica reactivity. So this is one of the known textures to cause alkali-carbonate reactivity, which is euhydrodolomites, dolomite minerals, which is the red arrows here, kind of quote unquote floating in a micritic mud matrix of limestone. So the typical reactive aggregates are argillaceous dolomitic limestones that cause alkali-carbonate reactivity. Now I say there's much less known about it, or much less understood about this reaction. So what people think for alkali-carbonate reactivity is that the dolomite de-dolomitizes and produces another mineral called brucite, and that brucite is what would cause the expansive properties of this. Other people argue that it's not really alkali-carbonate reactivity, it's alkali-silica reactivity that's happening, and there's just really fine clay-sized silica minerals in this micritic mud matrix of this limestone. So it is kind of an interesting topic to hear people discuss. I did see a presentation done by the U.S. Army Corps of Engineers about a year ago, and they said that they had a dam that experienced alkali-carbonate reactivity issues, and it caused their dam to expand like a foot or two or something like that. So they had to like saw cut joints to relieve pressures. And I'm not sure if I'm sure that dam is going to be replaced because of that issue, but it was an interesting presentation and just another thing to keep aware of when you're doing petrographic observations. If you believe ACR actually happens, or if it's ASR, you call it out anyways. You say there's a potential for it. All right. This is a good time to ask if we have any questions that have come in so far.
We have a few. One question that we had earlier was, over time, has there been substitution of the types of aggregate materials due to resource limitations? Have you ever seen that?
I would say no. Some people, I mean, it's based on your geographic location again. So, and typical producers or people who will want to buy construction aggregate will want to buy it as close to their project as possible to save costs on, trucking or railing it from somewhere else. That being said, if you need a really good aggregate, like for an airfield pavement, U.S. Army Corps of Engineers have very tight specifications for their aggregate that is used in pavements for their airfields. And if there's not good enough rock around, I have seen them ship it across like at least one, maybe two state lines to get that aggregate up there.
Wow, that's great. We do have one other question, Chris.
Sure.
For the petrographic analysis, do you do reflected light microscopy for opaque minerals?
We do, and it's not as intense as somebody who obviously practices that discipline more for like ore minerals and are trying to figure out what kind of grades they're looking at in an ore body. But we do reflected light microscopy just to try and identify if there's pyrite or pyrrhotite, things of that nature. We don't get any really crazy. I have seen millerite because they were using some of their waste product from a nickel mine as concrete aggregate, again, because of location and proximity, and they wanted to reuse that material. So we did see millerite. That was pretty neat, but that doesn't happen too often. Mostly it's just pyrite and some of the normal, I guess, gang minerals, I suppose you would call them in the ore world, but so it's not as intense as something like that.
Great, thanks for that. Do you have time for one more question, or should I hold those to the?
Sure, let's go one more.
Oh, one more. Okay, so this question is, does glass content of expanded aggregate cause problems?
No, because I think it does have a glassy texture, and it is. I haven't seen anybody report, and actually I've read a couple technical articles that typically it doesn't lightweight aggregate that expanded shale does not cause bulk alkali-silica reactivity in concrete. And I think it might have to do with it counteracting itself because there's enough glass where in enough aggregate used that it might not produce bulk. It might counter-react with the other particles, if that makes sense. But to the stuff I've read and the stuff I've seen, I haven't seen bulk distress from that. And from what I've read, that glassy texture in those expanded aggregates do not cause alkali-silica reactivity.
Great, thanks.
Okay, let's continue to our petrographic analysis of concrete. And we follow ASTM C856, which also includes ASTM C457. Now, C457 is how to perform hardened concrete air void analysis, and C856 is the standard for petrographic analysis of concrete. So this image here, this is of concrete under our stereoscope, and you can see each of these voids is actually purposefully air entrained concrete. So they have a chemical admixture that they will add to the concrete, and they need a certain percent, and it has to do with freeze-thaw durability of the concrete. In Minnesota, typically, like for our pavements, our DOT will specify like 5 to 7% air entrainment. This will help that concrete kind of expand and contract like a sponge almost during freeze-thaw cycles. And I have seen, I think they even spec like air entrainment like down in Georgia and different things like that. So it's very common to see air entrainment. So one thing we do is we'll do what's called a linear traverse using C457, and we'll measure each of these air bubbles, and then you do a bunch of calculations and it'll give you your percent air. So then you can see if it meets the specs that are provided for the job site or what have you. The other reason you might do it is maybe the concrete has strength issues, and the first thing you do is an air void analysis, and they might have way too much air in there. If you have a lot of air, like 12, 15% air, it can start to affect the strength of concrete. On the flip side of that, interior concrete slabs, like for flooring, they typically specify that air entrainment must be below 3%, and that has to do with different finishing techniques. So if they have some issues with the finish of the floor, and we do an air analysis and it's above that 3% limit, you know, they'll probably go back to the ready mix producer, the concrete producer, and talk about who's going to pay to fix the issue. But with this method, we also look for any micro cracks that might be in there. We can see different secondary deposits that might be in there that might affect concrete durability. I'll talk about alkali-silica reactivity in a second, and we can see that in the concrete as well. So I was talking about deleterious particles, and one of them being shale. In the Midwest here, we have some pretty nasty shales in our sand and gravels. This photo on the left here is of a interior floor, and all those circles are little shale pop-outs. And over here, these two photos are actually pictures from my driveway. We poured a concrete apron at our previous residence, and in that first winter, I was able to catch this pop-out actually happening, which was pretty awesome for somebody like me, because I think pop-outs are cool. Most ready-mix producers and aggregate producers will tell you they are not, because homeowners will call and complain and ask for their concrete to be replaced if it's too many pop-outs. But typically, standards do allow for a certain amount of pop-outs to happen in concrete. So anyways, I did catch this pop-out. After I took a photo of it, breaking apart the top mortar of the concrete, I dug out the particle, and this particle was a nice shale particle. And our shales are very absorptive. You can, and I have done this in front of a crowd of people, stick this shale to your tongue as a normal geologist would do, and it sticks right to your tongue, let go, and when you start to pull it off, it actually hurts because some of your tongue is absorbed into the rock. But they are nasty things. So with pop-outs, what can happen is that shale will absorb the water and hold it there, and then it might freeze and thaw and expand and contract, and then it just expands where the internal pressure exceeds the tensile strength of the rock, and then subsequently fractures the overlying mortar or concrete. So that's typically what happens with pop-outs. Now the other type of pop-out, this one up here we'll talk about again, just because this has become more and more prevalent, is especially sands that have fine aggregates or sands that have these shale particles. If they're near the surface of the concrete, and let's say you use this as an interior floor of a building, and then they put a nice flooring down, like terrazzo or some kind of epoxy floor, well, that kind of stuff is impermeable, so it will hold the moisture in, and moisture coming up through the slab might react with those shales and cause, it's called near surface alkali-silica reactivity, and it will cause those shales to pop, and all of a sudden you'll see blisters all over that nice floor. So some flooring manufacturers will actually tell the producer to prove that there's no particles like that in their aggregates before they will allow them to use their product, their flooring product. Other times the flooring product is put down and not knowing what the aggregate is, and you'll get these blisters, and then we'll take a look at it and see that these have caused some shale pops. So we also look at concrete in thin section, and I'm going to tell you why I'm going to say this, but one thing I want you guys to take away from this lecture is to not call cement sidewalk a cement sidewalk. It's a concrete sidewalk, right? Cement is a very finely ground manufactured product. It's that bag of gray powder, basically. And concrete is the combination of cement, water, rock, and sand, among other things. They can add different chemicals and whatnot, and supplementary cementitious materials. So each of these red arrows on this picture on the right are actual cement grains. These are A-lite Portland cement clinker particles. And what you're looking at is this middle piece, we call it the seed. This is the remaining alite crystal, basically. And this surrounding space around it is actually the hydration rim. So we can see that, and we can document what we think the hydration is, or the water cement ratio was at placement. And typically we're in about, 5/100ths of the water cement ratio. So you might say a typical average water cement ratio is 0.45. So we might say, okay, based on this and a couple other factors on the hand sample of the concrete, we think it was placed at a 0.5 to 0.55, even though it was specified to be a 0.45. That means the contractor added too much water. But so this will tell you if this seed is all the way gone, you say it's fully hydrated. If the seed, the crystal is still all there, it's low to negligibly hydrated. So you can kind of see the hydration as the concrete goes. Obviously, the older the concrete is, we've had concrete in here that has been several decades old, 50 plus years old. We even had one of the first pavements in here ever done in the US. These will almost be fully hydrated because they've had that long to continually hydrate. Almost all the concrete that you walk on is still technically gaining strength and hydrating. So the other thing we can see, this picture on the left, all these spherical particles are called fly ash. And if you're not familiar with that, fly ash is a byproduct of the coal burning process. And a lot of producers of concrete started adding fly ash into their mixes for a variety of reasons. One of the main reasons is these end up being glass spheres, and you can put them in there and you can what's called mitigate. They use it as mitigation to control alkali-silica reactivity from happening. Remember we talked about that gel that can happen from different quartz and silica minerals. Well, if they add fly ash in there, maybe 15% or 30%, there's all kinds of tests to figure out what percentage you should add. This can help mitigate and can kind of control that. So we can see the fly ash that's added, and we will give a percent of what we think is in there, and maybe the producer didn't specify any fly ash from happening. And we can see if they did or not. So add it. All right, here's the alkali-silica reactivity. You can see that that amorphous gel. This is a thin section of concrete. This up here is concrete paste. This is metamorphic aggregate with some of those reactive silica minerals. And this is that amorphous silica gel propagating and starting to crack up that concrete paste. On this slide, again, this is that alkali-silica gel. These are actually glass beads that were used as decorative aggregate in a concrete that was put on a side of a pool. Well, you need alkalis in the cement, you need reactive silica minerals, and you need water or moisture to cause alkali-silica reactivity. So if you have a highly reactive glass aggregate, you have alkalis in the concrete, and you're by a pool, so there's moisture available. It was not good. That sample, I think, is on our wall of shame. So here's a real life photo of what alkali-silica reactivity looks like in the field. Those classic characteristic cracking patterns. All that white you see is gel pouring out of those cracks. So it can be really destructive. Now, one thing to consider is that alkali-silica reactivity can take, upwards of 20 years to develop. Typically, you want your structures to last, I think engineers say, oh, we want this structure to last 75 years plus. So even at 20 years, that's still pretty young in its life. And they don't want this to happen because obviously they're going to have to replace it sooner than later. Some more field examples of ASR. This is a concrete sidewalk. Again, you can see that cracking that just destroyed this slab, this sidewalk here, and all that white filling in the cracks is is the amorphous silica gel. Again, here's some dams. Dams are obviously pretty susceptible to this if they use reactive aggregates. There you got that alkalizing the concrete, and they have a lot of moisture available. Again, you can see that alkali-silica gel in this upper right photograph image starting to pour out of those microcracks, those fractures. All right, so one other thing we can look at is fire damage in concrete. So we get these quite a bit. So we can tell if you should replace your concrete if it's been damaged beyond repair, or if you can salvage it. So typically, the 250 degrees to 350 degrees Celsius, pink to red discoloration of aggregate caused by oxidation of iron compounds in the minerals, and that's the first significant drop in strength of the concrete you'll see. And then we look for at 573 degrees Celsius, you get a volume change in quartz with radial cracking patterns around the quartz grains in the aggregate. And then if temps are in excess of 550 to 600 degrees Celsius, concrete is not structurally useful after heating in those kind of temps. So at that point, you definitely have to get it replaced. But we can do those isotherms on there and kind of map how deep that we think the fire damage did propagate into those concrete cores. Here's another one. A concrete core is exhibiting external sulfate attack, that white colored zone. The sulfate attack of this concrete was most likely caused by sulfate reducing bacteria. The anaerobic bacteria produce sulfur dioxide, which dissolves in water and then oxidizes to form sulfuric acid. So acid reacts with concrete very poorly because concrete is more alkaline. So you can see this pink stain here. That's what we call our pH indicator. And if it's pink, that means your concrete's pH is good. If it's not, that means it has carbonated or has some kind of attack has gone on to lower that pH. All right, so a few other projects that we've done. This is a columbarium, and at a cemetery. One thing you notice right away is that they have these nice, beautiful white marble panels, and these ones are starting to stain. One issue you can see right off the bat is that up here on the top in their concrete, you can see this white secondary precipitate. So they have water probably coming through this concrete, and that's most likely calcite. So you can see the water pattern flowing right down these tiles. Again, on this side, you just get a better view of those stains. So it had, that water was, the cause of this staining, or it helped it along anyways, and I'll show you what happened exactly. So this upper left photograph was what it should look like. That's a beautiful white piece of marble, nothing in it. And then we started looking at some of the other slabs with the staining, and from afar, you started seeing these little black dots everywhere. And then when you got closer, you could kind of see that stain kind of propagating out of those little mineral particles. So we were able to pluck some of those out, and we used X-ray diffraction, and that ended up being sphalerite, or a zinc sulfide. So even those tiny little particles, I'll go back one slide, caused those nasty stains on these nice white tiles just because they had that water and moisture coming from above and reacted and started to oxidize those minerals. This one, upper left, we'll start up here. These are sandstone, a very famous sandstone paver that was used all over the Northeast. We got a call from a contractor that said he installed these, and then he went back to clean them. And after he cleaned them, he started seeing minerals or something growing out of the rock. So he sent them in, and this is the photograph we got in the lab. The first thing I did was I don't know why I did it, but I just ran my finger over these spots. And when you say something is growing, obviously you should feel something, but I felt a recess. So obviously, whatever he was thinking was happening, it was the opposite. It was actually doing something to cause pitting. So we took a cross section of it, and those areas he thought were mineral growths or secondary growths ended up being like limestone mud clasts that were in this sandstone. And you can see a nice view of that up close. So I asked him what kind of cleaning product he used, and I'm not going to tell you the name of the product, but I will tell you the main ingredient was hydrochloric acid. And every geologist listening on this call should be able to raise their hand and tell me what hydrochloric acid does to limestone, because it is obviously a tool we all learned to use in our universities. So his cleaning product was starting to dissolve these and react with these lime mud clasts and cause this pitting. So the question becomes, whose fault is it? Was it the quarry who was producing this stuff, wasn't doing quality control and finding these mud clasts, or did the contractor use the wrong type of cleaning solution, but he didn't know those were there? I'm sure those two talked, but we were not privy to those conversations. Sometimes we do get into litigation. I actually have a litigation I was supposed to fly out to this fall or this summer, and it got postponed for the obvious reasons till next year. All right, here's another dimension stone project. These nice big limestone tiles, they were actually shipped in from Europe to the States and placed in a big patio in someone's backyard. Well, it started to experience all this cracking, and they wanted to know why. So they sent it to us. There is also an engineer in the field that did a bunch of engineering and field observations. We looked at the stone under magnification, and we found all these different planes of weakness. Like in this one up here, that's stylolite. A stylolite is like a pressure solution feature, and it can be a pathway for moisture to get in. So that's something we call out in a petrographic observation of dimension stone, is these potential planes of weakness. So stylolites being one of them, and this one started to fracture later. Another one is veining, or any microfractures or macrofractures that you might see in the stone. And we had this nice cross section here where you could document these fractures or these veins that are in there. And you can say that they were inherent in the stone because I don't see those cracks or anything going into the mortar setting bed below it. So we documented that and said that, you know, we see these planes of weakness, these potential planes of weakness that could have contributed to all this cracking problems. And apparently this stone is known to be very resistant to weathering, but the engineer in the field did say that there was bad engineering on site, like poor drainage. The homeowner never shoveled snow. It was in a climate where they got a lot of freeze-thaw cycles. So if you're not shoveling your snow, that snow is melting and then maybe freezing overnight, melting, freezing overnight, and gets trapped in these planes of weakness that we see. It can cause big problems. So it ended up being a combination of things. If the property was engineered correctly and had proper drainage, would the stone have survived? Maybe, you know, so it's one of those combination of things. You know, they have to deal with whose fault is it? Is it the stone's fault again, or is it the contractor who did all the drainage design and whatnot? So this one is, I did a C295 on this aggregate, and this was a nice quarried basalt aggregate. Started getting seeing these nice angular fractured particles, which you would expect out of a hard rock being crushed and produced. Well, then I started finding all these soft, rounded particles, and I made a thin section of it, and it was this image on the right. and it was like a mudstone or shale or something. And I was like, what the heck happened? So I called the geologist. This is from the West Coast. You know, sometimes for these quarries, we don't get the location of these quarries. We don't really have any knowledge of the geology of the area. I do my best to try and look at geologic maps, but it can't tell. Geologic maps, unfortunately, don't tell the entire story. But so the geologist sent me this picture of the quarry face itself. And you can see nice basalt on top, nice basalt on the bottom. And then he didn't have a scale, but that was an approximately 2 foot thick seam of shale or mudstone, whatever you have it, which was really nasty stuff, really soft and whatnot. And the geologist out there was explaining to me that happens because of abduction, you know, where the subducting plate, the top of the subducting plate will get scraped off by the upper plate and cause this intermixing of these ocean floor sediments and ocean floor basalt. So kind of cool to see that. All right, so this was an interesting one. This was a structure collapse. We do get involved in these. And so what happened was one of these walls, I think, just tipped over, and a couple people were actually killed. So it's super unfortunate, but we were flown down there. A couple of my colleagues went down there and they observed and documented people taking about 100 cores out of all this concrete to try and figure out where this structure actually failed. And a lot of different people were down there involved in this stuff. I guess it was a nerve-wracking situation with OSHA there and lawyers and this and that. But what you can see here is this was a pad for one of these piers, and the whole thing was supposed to be covered in a high-strength grout. And what happened was the grout, I'll show you. So it ended up being a grout failure that caused that to happen. So after looking at like 100 concrete cores and several samples of grout, we determined that the grout failed and it wasn't really what it was supposed to be. So you can see all this red ink is all microcracks that one of my colleagues had mapped under the microscope. Very tedious, but it definitely gets the point across that something happened. On this photograph on the right, you can see that the sand that was supposed to be in the grout is segregated. So there's barely any sand here in the middle. You can see all this plastic microcracks that happened from plastic shrinkage of the grout. So we determined that it was overwatered because of the sand segregation and the plastic shrinkage, and it was supposed to be placed in a monolithic placement or one placement, and it was probably placed in a few lifts. So that plastic shrinkage typically happens when it's drying out in a plastic state. So not good, but we were able to verify the problem and give our results to the engineering firm on site. So, all right, I think this is one of my last slides, and these are a couple of our most notable projects that we've worked on. And when the hijackers took the plane on September 11th and flew it into the Pentagon, there was an engineering firm on site who was a client of ours, and they had the president at the time of the Petrographic group fly down there and take a look. And they decided to evaluate like the structural beams and the columns for fire damage to see which ones they could salvage and which ones they had to replace. So they took about 170 concrete samples from those structural beams and columns. And I guess I wasn't here at the time. I was still in college when that happened, but apparently it was 3 weeks of very diligent, very long hours by our team at the time, because you could imagine they wanted get the results as fast as possible. And the other one is a homicide investigation that happened in Las Vegas. So a body was found in a concrete sarcophagus out in the desert. Somebody was jogging, I think, and found this. And they couldn't identify the body, because in those arid conditions, I think they decompose a little bit faster, possibly, or I can't remember, but they couldn't identify the body. So they sent it into us, and we took a look at the concrete, and we were able to kind of give a relative age of the concrete, which helped the police determine through the missing persons list, they were able to identify the victim because of that. And then we were also able to confirm that the concrete from the sarcophagus here matched the concrete on the murder weapon up here, this utility knife. So unfortunately, they did identify this woman, and they do have a person of interest, but they never were able to make an arrest. But I have seen this piece of concrete where the leg holes are in it, and it's very unsettling to see that in person. You can imagine why. But we were able to help out the crime lab, and they are at least able to identify the victim, which was good for the family. And with that, I'll close it out for, maybe we'll have time for some questions. I know that went a couple minutes over, but if you have any other questions, my email's there. Go ahead and take it down. Also, I try and post images that I'm working on that I think are pretty neat on my LinkedIn page. I call it the hashtag Petrography Monday. Give a little description. Been doing that for almost 2 years now, and people seem to like it. So with that, I just want to say thank you.
Great, thanks, Chris. We are running up against the hour, but I think we can take a few questions if you're okay with that.
Sure.
Okay, let me go ahead and share my slides here again. Okay, there we go. So we'll go ahead and take a few questions here. We've got quite a lot coming in, so thanks everyone for the great questions that you've been asking along the way. One question I wanted to ask you, Chris, that did come in and really speaks to students that are watching the webinar today is, what type of education is required for a career in forensic geology? Is there a degree program a student should pursue? Are there specific courses, or is it more of a combination of geology, engineering, material science? So what advice would you give students who are watching your presentation today?
Yeah, that's a good question, and I don't know too much about what universities are running for their programs now, if any geology programs touch on this stuff or not. Like I said earlier, my geology program did not touch on how aggregates and minerals react in concrete. So I guess what I would recommend is just check out geology. Definitely need some optical mineralogy knowledge to look down the scope and be able to identify minerals under the petrographic microscope. And an engineering background, some civil engineering courses in concrete and concrete making materials would definitely be a huge benefit. Also, chemistry, believe it or not, chemistry is a big thing because a lot of chemical reactions happen. We do have a chemistry department here that we work hand in hand with, and knowing about chemistry helps as well.
Great, thanks for that. I have quite a few questions, so just take one here at the end, just to kind of wrap it up. Can you talk about fossils? So can fossils such as radiolari, algae, and crushed stone cause problems in concrete? Have you seen that?
A typical fossil that's just been replaced by calcite or dolomite or whatever, what have you, for carbonate minerals, no, that doesn't really do anything. In one of my slides in the beginning, 69% of the crushed stone used in 2019 was carbonate aggregates. So a lot of fossils happen. I'll see a lot of fossils, and it's just part of the stone. What can happen though is if those fossils silicify, And I have seen, I think, I'm not like super up on fossil names and whatnot, but like diatoms and diatomaceous earth can have that silica reactivity. Diatomaceous earth can actually be used as a mitigation tool. And then I have seen some silicified radiolarian that can cause alkali-silica reactivity as well. But in general, fossils do not cause any issues in concrete.
Great, thanks for that. I think because we're over by a few minutes, we're just going to go ahead and wrap it there. So thanks everyone for your questions, and I'll be sure to send those along to you, Chris, so you've got that list. And then,
sounds good.
So great presentation. Thank you so much. Again, we'd like to thank JEOL for sponsoring the CEUs that will be issued to all attendees at today's webinar. JEOL electron microscopes and analytical instruments have supported scientific research and discovery for more than 70 years. And again, if you have any questions that were not addressed today, you can email them to us at GOLI@americangeosciences.org, and we'll make sure to send your questions along to Chris, or you can contact Chris directly as he gave you his contact information there. And so then this concludes our webinar for today. So thank you very much, Chris, again, for sharing your time and expertise and insights with us today. Fascinating topic, and I learned a lot, and know everybody did, so really appreciate that.
Great, thank you.
Thank you. So thank you everyone for joining us. We look forward to seeing you next time.